Kaons are the lightest strange mesons, meaning they consist of a quark-antiquark pair, where we only consider the up, down, and strange flavors. We can combine them in 4 possible ways, and by using the Gell-Mann-Nishijima formula, we can assign these quark-antiquark combinations to particles. These are called strong eigenstates, since they are created via strong interactions. Kaons are pseudoscalar particles, that is, they pick up a negative sign when we apply the parity operator. As for charge conjugation, particles change into their antiparticles, so K plus goes to K minus, K0 goes to K bar 0, and vice versa. The sign here can be chosen arbitrarily and has no impact on the following physics. It is important to notice that the kaons so far, as described by their quark structure, are no CP eigenstates. For an eigenvalue equation, the state has to appear on both sides of the equation. In the following, we will only focus on the electrically neutral kaons and construct such CP eigenstates. Let's define a new state, K1, as the difference between K0 and K bar 0. A CP transformation exchanges K0 with its antiparticle while picking up a minus sign. This gives us K1 again, hence this is an eigenstate. A similar calculation for K2 shows that it is as well an eigenstate, but with negative eigenvalue. Neutral kaons mainly decay via weak interactions into 2 or 3 pions. Pions are the lightest mesons. They consist only of up and down quarks. Each pion has a CP eigenvalue of -1. If we assume weak interactions to be invariant under CP transformations, then the CP eigenvalue doesn't get changed during a weak decay. Therefore, the K1 can only decay into 2 pions and the K2 only into 3. This way, we have the same CP eigenvalue on both sides of the equation. K1 and K2 are called CP eigenstates. But what about experimental findings? As it turns out, 3 pions have approximately the same mass as 1 kaon, so there's only a small range for the kinetic energy of the resulting pions, which prevents this process to happen often. For a decay into 2 pions, their kinetic energy can be in a much wider range, rendering this process more probable. For this reason, experimentalists see 2 types of kaons in the lab, a short-lived one called K-short and a long-lived one called K-long, which lives approximately 600 times longer than its partner. The propagation in the lab tells us that they have a well-defined mass, since time evolution in quantum mechanics is, in the simplest case, due to an imaginary phase depending on the energy, which relates to the mass. Let's recap. We're looking at neutral kaons in 3 different basis systems. We have the strong eigenstates based on their quark structure. Next, the CP eigenstates, which we constructed to fulfill CP eigenvalue equations. Finally, the mass eigenstates having a well-defined mass in order to be the ones that propagate. How are the mass eigenstates related to the others? Remember that K1 and K2 are distinguished by the number of pions they decay into. We also know that a decay into 3 pions is not very likely to happen, so it makes sense to identify K1 with K-short and K2 with K-long. This means that K-short and K-long must be CP eigenstates with the same eigenvalues as K1 and K2. In 1964, Christensen, Cronin, Fitch and others performed the following experiment. They let a neutral kaon beam propagate in a long tube. Since the K-long travels much farther than the K-short, they arrived at an arbitrarily pure K-long beam when reaching the detector. Much to their surprise, they sometimes measured a decay into 2 pions. This means that a K-long decayed into 2 pions, and the CP eigenvalue on both sides of the equation didn't match up. Nowadays, we have 2 possible explanations for this. First, we could just accept the fact that a K-long, that is a K2, can decay weakly not only into 3, but also into 2 pions. This would violate CP symmetry in weak interactions, and we call this the direct CP violation, because K2 clearly has an CP eigenvalue of -1, and 2 pions certainly have a CP eigenvalue of +1. Or, secondly, we redefine the propagating states K-long and K-short to include a small part of the other CP eigenstate. Then, the K-long can mostly decay into 3 pions, but also sometimes into 2. However, this way, K long is no longer a CP eigenstate, since one part transforms with a minus sign, whereas the other doesn't. If a process is said to be invariant under a transformation, then both the initial state and the resulting state have to behave the same under this transformation. This clearly isn't the case if, on the one side, we have an eigenstate and on the other, we don't. And this is what's known as indirect CP violation. Thanks for watching. If you like this video, subscribe to get more physics every week. That's pretty much it. Bye.